Good morning, everyone. Welcome to today's presentation. And welcome to the set of integrals that everyone claims is easy and obvious. And is obvious especially from symmetry and invariance. Made this first in classical electrodynamics, and at first then when I looked at them, I worked so hard and intensely. I never saw any symmetry. Well, so today I'm going to be proceeding by a method. I'm borrowing a leaf today from F.P.E. Chen's book. The book is on Relativity, Gravitation, and Cosmology, a basic introduction. F.P.E. Chen. I think I should write the name of the author. F.P.E. Chen. Together with another guy, I've forgotten exactly. Actually, this book I just made reference to, this guy alone was the only author. But I just wanted to make mention that they had another very popular and good book in quantum field theory, authored together with this guy. So the same F.P.E. Chen of that book is the author of this one. So I'm just going to use specifically the method I believe could be used to show some of these integrals. Now, first of all, if you look carefully at these integrals, what we're going to try to do, for instance, is to try to calculate. And one other thing I think I should do is to say, for instance, that maybe put in bracket here that theta ranges from 0 to pi, and that phi itself, of course, 0 to 2 pi. So maybe that's one thing we can tell right now. So at the moment, I can decide to just make a choice, choose the first one. In order to prove this, maybe I wouldn't do everything, but let me just attempt calculating for n sub 1 d omega. Of course, the ik, also maybe something else I should say is both I, j, iota, and kappa all range from 1 to 3. Yes, they all range from 1 to 3. So the n sub I here denotes the situation whereby I could be either 1, 2, or 3. So in this case, I'm choosing the case for which is 1. And that means this value here, as you can see from the beginning. And so, of course, let me start from the beginning, 0 to pi, 0 to 2 pi. And then again, I guess one other thing I didn't give at the beginning is the fact that d omega is the same thing as sine theta, the theta, the phi. Okay, so having said that, so because of this sine theta, I'm going to have instead sine squared theta because of this sine theta here too. Then I'm going to have cos phi, then the theta being the first one here, and then the phi with the second interval there, integration interval. So what we can do at this moment is to sort of factor them out like this, the theta, and this 0 to 2 pi of cos phi, the phi. Of course, we can tell that this is pretty much easier to perform than the first one. So what we can just do is, for instance, consider the fact that this is the same thing as the integral of sine phi, 0 to 2 pi. Now, the sign of the integral multiple of pi is 0, sine 0 is 0. So because this is 0, the whole integral here is 0. And of course, the same thing could be said of this second one, omega, and I'm using again n sub 2 here, which is sine theta, but sine phi instead of cos phi here. Again, because this has a sine theta, I'm going to have 0 to pi, 0 to 2 pi. This then will become sine squared theta because I have a sine here and a sine here. Then I have here with me sine phi, and this, for instance, is going to give me the theta, the phi. And then factoring again, just like I did before, what I will get, for instance, is here 0 to pi of sine squared theta d theta, 0 to 2 pi of sine phi d phi, and of course, just like we did before, this is going to be minus cos phi, 0 to 2 pi. Of course, I can simply just pull out the minus. The cos of 2 pi is 1, and of course, you know the cos of 0 is 1. So I'll have 1 minus 1. So because of that, again, this is 0. You can take my word for it, or just feel free to show also that it's true when you substitute n sub 3 to be equal to cos theta, and of course d omega to be equal to that. You'll be able to show that that is true. So in essence, we have been able to confirm or show, for instance, that n hat of I d omega in general is equal to 0. So these are the conditions under which that is equal to 0. Now, looking at the next one, which we'll deal with about 3 of them. Okay, we may just have to do that once. In fact, what this will be, for instance, is to consider the fact that when I said n sub I, n sub j, n sub k, d omega equal to 0, this is for I not equal to j, none of them is equal to the other. So we have to show this just once, just 1, 2, and 3, d omega. Combining everything like we'll do 0 to pi, 0 to 2 pi, n sub 1. So let me try to do this all in one blow. Again, writing d omega to be equal to sine theta, d theta, d omega. You realize again that we have to multiply this, and this, all 3. So I'm going to have sine here times sine, which will be sine squared theta, but then again I'm going to have here sine cubed theta, and then I'm going to have a cos theta following it, and then of course I'll have a cos phi and a sine phi grouped together like that, d theta, d phi as usual. This is same thing as 0 to pi, sine cubed theta, cos theta, d theta, and 0 to 2 pi of cos phi, sine phi, d phi. This again I can write, for instance, as 0 to 2 pi. Okay, now, depending on how I want to do this, I could say, okay, for instance, to get this, okay, well, I will leave this one instead, and then use the cos theta. So I'm going to say that, for instance, this is sine phi, d of sine phi. And of course, if you recall, if I differentiate sine phi with respect to phi, I'll simply get cos phi. In other words, d of sine phi is the same thing as just cos phi d phi. So I've combined these two to obtain this. And so these are now my new variables. In essence, again, this simply just looks like this. Sine squared phi all over 2, 0 to 2 pi. Again, so this operation does not affect the limits. So that at this point, you recall again that sine 2 phi is 0 and sine 0 is 0. So again, this is 0. I did not touch this one, so this is 0. Okay, again, we don't need to do anything else. And with this, then, we have been able to show that this is 0, which again proves just what we've stated right from the beginning. And we are done with that. This I'll leave for later because I think, I just hope I do not forget anyway. But I'm going to do this one first because I think I'll need something there for you. So now, moving forward, we can decide then to perform. So what I've got here is n sub I, n sub j, d omega. We want to show that this is ij. Well, in other words, it means when I is not equal to j, we're expecting 0. In other words, ni, nj, d omega is equal to 0 for all I not equal to j. So if that is the case, let me choose a situation whereby I have n1, n2, d omega. This then will be 0 to pi, 0 to 2 pi. I'm choosing n1 here, and that gives me a sine squared theta. And then, okay, no, sorry, it should be cubed because I'm going to be bringing in again this old friend of ours that I keep erasing, the theta, the phi. So it will be cubed because this sign here is going to need this sign and that sign. So I'm going to now combine cos phi and sine phi. So I have here with me sine phi, cos phi, but then the theta, the phi. Again, so this is going to give me 0 to pi, 0 to 2 pi. Okay, no, I would like to really group this in a way that will be easier for me. So now I'm going to do 0 to pi. This will be sine cubed theta, the theta, and then 0 to 2 pi, sine phi, cos phi, the phi. And of course, if you recall, this again we could write as 0 to 2 pi, cos, okay, no, I would like to leave the sign. Yeah, cos phi, but then d of if I did that, then I'll have to get a minus sign. Well, it doesn't matter. Let's just go whichever way that works for us. We're going to get a minus sign here. That is, nope. This is just pretty easy. So it's just like what we just did a few moments ago. If I left sine phi in here, then I'll be differentiating sine phi exactly. So because when I differentiate sine phi, I'll get cos phi d phi. I don't need to add any minuses to that. Again, this will simply look like this in the end. Sine squared phi all over 2, 0 to 2 pi. Then again, for the fact that this becomes 0, we can see that this is 0 already. Please, again, since we have shown this severally, you can just take my word for it, or feel free again to show that this is the same thing as n, I guess now 3 and maybe 1, the omega, that all these two are 0, of course. You can show this just like we've shown for this one. So in other words, this has completed the proof for the fact that for when I is not equal to j, this will give us 0. So I'm going to try to perform the case for which they are equal, and we are expected to get 4 pi over 3. Okay. And again, doing that, we just start with the very first one, which is n sub 1. So if they were to be equal, for instance, and both are equal to n sub 1, this will be squared, the omega. Then this again will be simply 0 to pi, 0 to 2 pi. N sub 1 is squared, multiplied by the sine theta here. So this is going to give me sine cube theta, and I'll have cos squared phi here. And having gotten that, again, then what follows, of course, will be just nothing else except the theta and then the d phi. So this will give me 0 to pi of sine cube theta d theta. And then I'm going to have here 0 to 2 pi of cos squared phi d phi. Okay, now looks like we've got a problem. This is not something that looks like we can reduce to 0, and it's not just so. But dealing with this factor, for instance, 0 to 2 pi of cos squared phi d phi is same thing as 1 all over 2 integral of 0 to 2 pi of 1 plus cos 2 phi d phi, which, by the way, is 1 all over 2, and I'm going to integrate that, will give me that. And this would be simply plus sine 2 phi all over 2, 0 to 2 pi. Evaluating that, I'm going to have here with me just 2 pi for the, 2 pi for the first one, which is that. Sine 2 pi is 0, sine 0 is 0. So in the end, of course, when I do the minusing, I'll substitute 0 for both sides again. So all I've got here is pi for this one. So this particular factor here gives me a pi. And now I have to contend with the next term over there, which is the integral of sine cube theta. And the integral of sine cube theta, of course, this is 0 to pi, sine cube theta d theta, as usual. You can say sine theta, sine squared theta d theta. The reason being that I just want to say this is the same thing as, okay, no, not cos. So I can take this to be sine theta, and then this is going to be minus, of course, sine theta, but cos squared theta d theta. Yeah, by simply substituting 1 minus cos squared theta for that. Now, if I did that, I have a d theta following this one. The first one will be sort of minus cos theta, because differentiating this is what will give me that. Then I'm going to have a minus sign here, an integral of 0 to pi of sine theta cos squared theta d theta. At this point, again, okay, well, I'm going to get a minus sign. It wouldn't matter. For instance, this as a whole will be the same as 0 to pi with a minus sign, but cos squared theta, this time around it will be d cos theta. The minus sign is there because if I differentiate cos theta with respect to theta, I get a minus sine theta d theta, and the minus is, of course, going to be cancelled by this minus sign here. So in other words, Okay, let's look at this one. Like I said, usual, I could just pull out the minus up front. Cos pi is minus 1. Cos 0 is 1, of course. So I'm going to have minus 1. In essence, minus 2 in here, so which is simply going to be 2 down here. So I'm going to have 2 here. But recall that I have a minus here, so this will make this a plus, an integral of pi. Okay, so I think I should just evaluate that integral already. So instead of this, I'm going to get something like cos cube theta all over 3, but 0 to pi. So at this point, cos 3 theta, of course, means cos theta raised to power 3. So substituting theta to be equal to pi in that expression, we get minus 1. So minus 1 raised to power 3 is just another minus 1. Then minus another 1 that we will obtain when we substitute theta to be 0 for cos here. So I'm going to have minus 1 over 3, minus 1 over 3, which is minus 2 over 3. It therefore means, in essence, that I'm going to have 2 here, minus 2 all over 3. And if you were to perform that, of course, you can see you're going to have 6 minus 2 over 3, and this is 4 all over 3. So in essence, this gives me a 4 all over 3. So that in the end, this is indeed 4 pi all over 3, just like we expected. In other words, again, you can just take my word for it, but feel free to show some very fun exercise if you think this is an exercise. So just show that this is also the same thing as 4 pi all over 3. In other words, we've just established that whenever I is equal to j, we are either going to have something like this, like that, or like that. Or if they are not equal, then we'll have something like the first one we solved, something like n1, n2, d omega. Or we may have something like integral of n2, n3, d omega. And we showed in both instances that all that will give you 0. So in essence, we have just been able to show indeed that this is equal to that. So with that then, I'll move forward. I think one thing I was thinking I may need is, well, let's just see if this will be useful so that I don't have to do this all over again. The theta is going to be 4 all over 3. And also the fact that, so let's just see if this will be of any use instead of repeating it all over again. The phi gave us pi. Yes. Okay. So now, moving on to the next thing, which will be the fourth one here. Okay, well, maybe I shouldn't just jump that yet. Excuse me, please, I need to get to better mathematics. So, looking at this expression, I better just do this one first, then we can just go ahead to confirm the other one. So, this one says n sub I squared, n sub j, n sub k, the omega equal to 0. Of course, here we mean that these three are not equal. So I can simply just do the obvious, n sub 1, n sub 2, n sub 3, the omega. Let's see what that gives us. And in this case, then I can say, well, of course, I'm going to be squaring this first term. And if you recall, I'm going to multiply it with this and that. Then, of course, remembering that d omega again is equal to sine theta, d theta, d phi. So at this point in time, the square of this will give me sine squared theta times this will give me sine cube. Yes, and then times that will make it, this will be sine 4 theta, I guess, so 0 point, let me do this, 0 to pi, 0 to 2 pi. So I hope I've not jumped any such. So I have a sine theta coming from here, a sine squared theta, and then multiplied by that give me sine 4 theta. Okay, now next, of course, we can see that apart from sine theta, we have also cos theta, which comes along from this one. Then combining the phi factors, I'm going to have cos phi. By the way, the cos phi will have to be squared because it was part of this. I squared this at first. Then I'm going to have sine phi. And then, of course, following that is the fact that I'm going to have, okay, so simply the theta, the phi. We haven't missed anything yet, I believe. Okay, so at this point in time, what I have then is going to be 0 to pi, sine 4 theta, cos theta, d theta, 0 to 2 pi, cos squared phi, sine phi, d phi. Okay, I guess I'll simply just focus on this. Hopefully it will be simpler, and then I won't have to bother about that. That's, of course, if this is 0. Okay, now this again, like I said before, my only move therefore is to write this as minus of 0 to 2 pi cos squared phi d, but then of course phi. So that when I differentiate this, I get minus sine phi, which is cancelled by this minus. This is what I get for this. And this in return will mean cos cube phi all over 3, 0 to 2 pi. And of course, sine 2 pi is 0. Yes, I mean, cos 2 pi is 0, but cos pi itself is minus 1. So since cos 2 pi isn't 0, please, cos 2 pi is 1, then cos 0 is equal to 1 either. So 1, 2. So in the end, I am going to have some 1 minus 1. Of course, the cos cube phi here simply means cos phi raised to power 3. So 1 raised to power 3 is still 1. In the end, this is 0, so this proves that to be 0. So if we have a situation whereby we have 2 of them equal and the other 2 different, we get 0 again. So getting that out of the way, we're going to look at what is a little bit more fun. And we can do this in 2 steps. At this point in time, we'll have to look at the expression given to us on the right-hand side. First of all, you should take a look at this. What this is saying is, definitely one of these have to be obeyed, and whenever one of these is obeyed, the other ones are just not going to work out, or they wouldn't be obeyed. For instance, if I say I is equal to j, then that's what it is all along. J is not equal to m, and I is not equal to iota, so this has to be 0, because I've already said I to be equal to j. If I said I is equal to m, iota is equal to m, then of course this is 0, because what I said was m equal to iota. Or I could choose this one and say, okay, well, I is equal to iota. Then it means this is 0 because I is not equal to j. What I choose was this. So in other words, in order to evaluate this, for instance, this is I, n, j, n, iota, n, m, d, omega. What I will have to do, for instance, is to choose a situation whereby any one of those 2 are equal. For instance, I could choose this to be equal, or these 2 to be equal, so that in the end, what I may calculate may be I squared, ij squared, d omega. And this really will be how I'm going to solve this. In other words, I could start with the example of saying, for instance, n sub 1 squared, n sub 2 squared, d omega. Again, notice that this is the only way you can proceed in showing this, because all of these conical deltas are selecting one of the possibilities, and whenever one of these is obeyed, the others automatically become 0. So in this case, for instance, I'm going to say, well, n sub 1 is squared. I think I will be very explicit with this one to avoid missing anything. So this is going to give me, first of all, sine squared theta, and that will be cos squared phi. And then what is following it is going to be sine squared theta, sine squared phi. Then, of course, there is the sine theta, the phi. I'm trying to factor this. I have a sine squared phi, and another sine theta. Sine squared theta, sine squared theta. So this is sine raised to power 5 theta. And then, of course, in this case, I have no cos theta. So this is what I have, the theta. 0 to 2 pi. Now this is going to be cos squared phi. And this is sine squared phi, the phi. Okay. At this point in time, I'm just going to take this one factor after another. For instance, in this first case, I can say, for instance, 0 to pi sine 5 theta d theta. One way to proceed by this is to try to give this to be equal to, say for instance, 0 to pi sine cube theta sine squared theta d theta. And if this works out, it means I can write it further as 0 to pi sine cube theta 1 minus cos squared theta d theta. And this, of course, gives me a 0 to pi sine cube theta d theta minus here an integral of 0 to pi of, again, sine cube theta, but I have now with me cos squared theta d theta. Okay. Now, one more thing we'll have to do again is to see how to resolve this. First of all, you can see already, yeah, we did have a need for this, so I wouldn't have to do this all over again. So you can see that that alone will be 4 all over 3. If that is the case, the next thing is, so I'm not going to, let me erase this place because what we're calculating is that. So I'm going to just focus on the second term here, which is sine cube theta and cos squared theta d theta. And this could be expanded by saying, for instance, 0 to pi. Okay, let me try something here. 1 minus cos squared theta again inside of this place. And then I have another cos squared theta here, d theta. Looking at this, you can see, for instance, that, so what I did was to have splitted this into sine theta, sine squared theta. Then the sine squared theta I changed to 1 minus cos squared theta. And of course, I still have my cos squared theta over there. Then this gives me, for instance, 0. This gives me, for instance, 0 to pi of sine theta cos squared theta d theta minus integral of 0 to pi again. I'm definitely going to have sine theta, but cos raised to power 4 theta d theta. I guess at this point things are easier because I can write this now as, say, minus 0 to pi of some cos 4 theta, but then d of cos theta. Yes, because when I differentiate cos theta, I get minus sine theta, which will cancel that, and we're back to just sine theta. And the same trick, of course, is going to apply here. 0 to pi, this will become cos squared theta, but then d, so I'm going to get a minus sign. D of cos theta, right? Exactly. So at this point in time, we can see that this one is going to cancel that. So let me not fuse around, so that that will simply be plus, because the two minuses will multiply themselves. And this, for instance, will become, so sorry I'm doing this, all over 5, 0 to pi. And this, of course, will be, okay, I have a minus sign following me, so it will be minus of cos 3 theta all over 3, but 0 to pi. I'm just trying to avoid erasing anything that we may have need for. So at this moment, we can see already that this cos pi is minus 1, and raised to power 3 is still minus 1. So I'm going to have minus 1 over 3, minus 1 over 3, which is minus 2 over 3. But then plus what is inside here, it becomes plus 2 over 3. In other words, let me just put it, so I have some 2 all over 3 for the first term. Remember, I had a plus here. Now the second term is what I'm calculating from here to here down to this point. Now at this point again, I'm going to have cos of pi is still minus 1, raised to power 5, which is an odd number, is still minus 1. And then there's cos 0, which is 1. So minus 1 over 5, minus 1 over 5 is going to give me minus 2 over 5. So in that case, then what I'm going to have here is minus 2 over 5. And then I have here with me an LCM of 15. And you can see, of course, that this is going to give us 10. Minus, here we're going to get some 3 multiplying that. So this is going to give me 4 all over 15. And by the way, this result is just for this one, if you recall, which is that one. But I had 4 over 3 here, so this is going to be 4 all over 3 minus 4/15. So another common LCM again. We are going to have some 5 times this. So this is going to be 20 minus 4. So 16/15 is what we get for this one. That's interesting. 16/15 is what we have obtained for sine raised to power 5 d theta with this integration interval. Now, looking at the next factor. Okay, so I think I can erase what led to this result. Now, this factor here, which is 0 to 2 pi of cos squared phi, sine squared phi, the phi is going to be equal to, now if you look at this carefully, so what I'm going to try to do is this. I'm going to write this to be 1/4. I'm going to explain where that is coming from. Of course, this can be written as 1 plus cos 2 phi. And you recall this next one can be 1 minus cos 2 phi. So from trig, each one of these has 1/2. So this has 1/2 that, and this one has 1/2 that. And this simply looks like the difference of two squares. So this is 1/4, 0 to 2 pi, then 1 minus here. I'm going to have cos squared, but 2 phi, the phi, by difference of two squares. I have 1 plus one thing, then 1 minus the same thing. I combine it, and that's what I get. Okay, but something also interesting could happen here. Take note that I could write cos squared 2 phi, the same thing as 1/2 again, but then 1 plus cos 2 times what I had before as my theta, which is 2 phi again. So this is same thing as 1/2, 1 plus cos 4 phi. I hope that is clear. Just see this as some theta. Then, of course, this is the theta. But we know what the theta is. The theta is 2 phi. And so we are down here. Okay, now with this then I can say, if that is the case, so what I'll try to do first of all,